This is Calculus 2 class. We're gonna study divergence and integral tests. Today, we are going to strengthen our toolkit for deciding whether infinity series converge or diverge. We start with divergence test, then move on the integral test. And finally, we'll see how we connect it to the important family of series called the P-series. Before I introduce divergence test formally, I want to see series and sequence. So there is some relation between series and sequence. AN is a sequence. We want to find sum of AN. Before we find the sum of AN, first I want to find the limit of sequence. Limit of sequence is going to be AN is 1, so that's going to 1 because A1, 1, A2, 1, A3, 1, A4, 1. That's the sequence go to the 1. Now, let's talking about series. Sum of all the sequence, which meaning is sum of 1 infinite times. What's going on? I visualize partial sum first, guys. Partial sum gonna be, here is n equal 5, which meaning is we're gonna add 5 terms. That's gonna be 5. S to 10, meaning is you add 1 10 times. That's gonna be 10. S15, you add first term to the fifth term. That's gonna be 15. S20 gonna be, what do you have there, guys? That's the 20. S100, you add 100 term. That's S100 is 100. Partial sum is increasing. We're gonna see this limit gonna be infinity. Another way say infinity series gonna be divergent. So what do you see here? Sequences never shrink. They stay whole 1. Sum of all the sequences can be converged, diverge. That's the first example and first relation between sequence and series. If sequence is not shrink, does not shrink, the series gonna diverge. We have another example, the relation between series and sequence. Let's have AN is 1 over 2n. That's the geometric sequence. We consider geometric series. So that's the geometric series. AN gonna be geometric sequence. What is the ratio? Ratio is 1.5. You know that AN going to 0, also geometric series gonna be converged. This case, you see very important information. AN sequence isn't getting shrink. Okay? Then series gonna be converged. Previous example is sequence is not going to 0, not shrink. That just stayed 1. Series gonna be diverge. This time, guys, this time. Sequence going to 0, series going to 0. Look at the third example. So this is a sequence. What's the behavior of this sequence? Guys, this one is shrink. AN going to 0. That's getting smaller and smaller. What is infinity series? So I visualize of this series. So let's find S10. S10 meaning is you're going to add from first term to the 10th term. That's meaning is 1 plus 1.5 until 1 of 10. So I calculate S10 right here. That's going to be 2.93. Now I want to calculate S100, which meaning is you add 1 to 1 over 100, I calculate that's partial sum S100, 5.18. Okay, let's do more. You add 1,000. S1,000 gonna be 7.49. Keep going, guys. 10,000. S10,000 gonna be 9.79. You have more, guys, okay? 100,000, you will see that number is 12.90. So partial sum gonna be, guys, slowly increasing, which meaning is limit of partial sum gonna be infinity. What is different from previous example? Previous example, an going to 0, 0 is gonna be converged. But this example say, even though sequence is going to 0, 0 is gonna be diverge. This divergence test. I'm gonna give the divergence test formally. General term, sequence of general term not going to 0 or limit does not exist, then series is gonna be diverse. So sequence, limit of sequence is not going to 0. Never shrink or limit does not exist, series is gonna be diverse. That doesn't mean, very careful, we read warning sign. Limit of sequence is going to 0. We have example, right? Limit of sequence going to 0 doesn't mean series is going to be converged. It might be converged, it might be diverged. You have to use in different tests. What you guarantee from this divergence test is limit of sequence not going to 0, limit of sequence does not exist. That's going to diverge. So let's have example, guys. Here is divergence test. Divergence test you're gonna use first to determine if a series is gonna be converged, diverged. So first you have to find an. What is the sequence? This series sequence gonna be here. This one is a sequence. So an gonna be n squared over 5n plus 1. So we're gonna find the limit of a sequence. Let's check it. What is the limit of an? So this is a fraction form. We can use L'Hopital rule because top going to infinity, bottom going to infinity. Take derivative of each. N squared gonna be 2n. 5n plus 1 is 5. So you see, limit n approach to infinity, that's 2n over 5. So this limit going to infinity, it's not 0. So you're gonna say that series gonna be diverse. General term not going to 0, that series gonna be diverse. Another example is right there, guys. That series we find an. An gonna be 3n plus 5 over 2n minus 1. Find the limit of sequence. Then this fraction, infinity over infinity, depreciate, numerator, denominator. We have 3 over 2. The limit is 3 over 2. It's not 0. We're gonna say this series gonna be diverse. So diverge tests, they give series gonna be diverse if general term is not going to 0. Another example, this one, negative 1 and n. An gonna be negative 1 and n. That's alternating. What happened, guys? We want to find the limit of an, which meaning is the first term is negative 1, 1, negative 1, 1. Limit does not exist. Series gonna be diverse. So divergence test give the idea series gonna be diverse if limit of sequence is not 0. I emphasize one more time. Limit of sequence is 0 doesn't guarantee series is converged. We have to do another test. Now move on to another test. So before I introduce integral test, let's have this example. I want to determine if this series converges, diverges. So I want to illustrate what it looks like summation n equal 1 to infinity 1 over n square. So you see an is 1 over n square. You can find the function which is related to this sequence. That's gonna be fx is 1 over x squared. So I sketch it. fx is 1 over x squared. Now, what are you going to do? I'm going to draw the rectangle. Base going to be 1 each time. So you see, I have base is 1. This is a height. So I want to draw the rectangle under the curve. Then find the area of a rectangle, guys. So first one is, we want to find the area of this rectangle going to be x value is 1, y value is 1 when you plug in the here. Height gonna be 1, base gonna be 1, area gonna be 1. That's we have 1 there. Second rectangle, I sketched the rectangle below the curve. Now you find this point. That's gonna be 2 over 1 over 2 square. Height gonna be 1 over 2 square. Base gonna be 1. Area gonna be 1 over 2 square. This one is the second term. Same thing is next rectangle. I find the point on the curve. That's the 3. 1 over 3 square. Find the area. Base gonna be 1. Height gonna be 1 over 3 square. Area gonna be 1 over 3 square. So that's the third term. So on. That's I draw the area of each rectangle right there. Fourth rectangle. You find the area 1 over 4 square. Fifth rectangle. 1 over 5 square. What kind of relation between this area to the area below the curve? Now, guys, I want to compare infinity series and improper integral. What is represent this infinity series? So here, infinity series represent area of a rectangle below the curve. What is represent this improper integral? That's the area below the curve 1 to infinity. So I can rewrite it. This one is area below the curve. This is sum of area of all rectangle. This one is area below the curve. Which one is bigger? Definitely what, guys? Right side is bigger. That's the gap is right there, guys. Okay? Now, let's find the improper integral first. What's the value of this one? Let's review improper integral one more time. 1 to infinity 1 over x squared dx. That's definition is 1 to t. T approaches to infinity 1 over x squared dx. And t derivative 1 over x gonna be negative 1 over x, 1 to t. I plug in the t, I plug in the 1 there. Limit t approach to infinity, negative 1 over t plus 1. When, as t approaches to infinity, 1 over t going to 0, limit of this is 1. Another way, improper integral is 1. So now, infinity series, sum of infinity series right here. This sum of infinity series, 1 plus integral 1 to the infinity 1 over x squared dx. You find the improper integral value, that's going to be 1. So this one is 2. You notice this sum of infinite series is less than 2. Then you're going to say that's going to be converged. They have some value. We don't know exactly what, but at least we know that's converged. Let's have another example. This time we're gonna use sum of 1 of n, series of this. 1 plus 1.5, 1/3, 1/4, 1n. We already know this is diverge. So I'm gonna prove this diverge by using this visualization one more time. First, what kind of function is related to this 1 over n? That's gonna be 1 over x. I'm gonna sketch 1 over x. This time, you're gonna draw the rectangle above the curve. First one is right here. Then you're gonna see area of this rectangle. You're gonna move here is 1 and 1. Area of this rectangle is gonna be 1. Guys, make sense? Second rectangle, that's the first term. Second rectangle, I sketch it. You have this point. That's going to be 2, 1.5. You have area, that's the 1/2. That's going to be second term here. Third rectangle, right here, rectangle is this point. 3 and 1/3 area gonna be 1 times 1/3. That's gonna be 1/3. That's gonna be right here, third term. So on. Right there, 1/4, 1/5. Now, we're gonna compare this total area of rectangle and area of under the curve. Now let's compare to series and improper integral right there, guys. Look at this. We know sum of infinite series represent total area of rectangle. Here it is, guys. Here it is, right here. This one is represent improper integral. That's area under the curve, 1 to infinity. Now, let's write it. Summation n equal 1 to infinity 1 of n. That's represent the sum of total area of a rectangle. This one right here is area below the curve. Which one is bigger? Rectangle above the curve. So left side is bigger than right side. First, I want to evaluate improper integral, guys. How can you evaluate the improper integral? So, using definition of improper integral, t approach to infinity 1 to t 1 over x dx. What is the antiderivative 1 over dx? Gonna be ln x. You plug in the 1 and t, that's gonna be ln t, ln 1. ln 1 gonna be 0. ln t approach to infinity. T approach to infinity. So this improper integral going to infinity, divergence. So we compare the series and improper integral right there. The value of improper integral infinity, which meaning is divergent. This sum of series also greater than infinity, which meaning is they can be converged. That's gonna be diverge. Here's the, I'm gonna introduce formally in integral test. Integral test condition is right here. Positive, continuous, decreasing over the sum interval. an sequence represent value of a function, then series gonna be converged, improper integral converged, series gonna be diverge, improper gonna be diverge. But here is a very important thing, guys. You find the value of improper integral L does not guarantee sum of series gonna be L. Only this test give us series gonna be converged, improper integral converged, improper integral converged, series converged, improper integral diverge, series gonna be diverged. That's it. We don't know sum of series. Let's have first example about integral test, guys. Integral test, we have this side, this infinity series converge, diverge. The first thing you have to do, find f of x, which is related to this sequence. So you can guess fx gonna be 1 over x squared plus 1. I sketched this function, decreasing, continuous. So we wanna do improper integral 1 to infinity. So we wanna try 1 to infinity fx dx. Let's figure it out. So 1 and infinity 1 over x squared plus 1 dx. That's improper integral. Use the definition of improper integral. T1 and t 1 over x squared plus 1 dx. T approach to infinity. Find the antiderivative 1 over x squared plus 1. That's the arctangent. Arctangent x 1 and t. You plug in the t, arctangent t. You plug in the 1, arctangent 1. Arctangent 1 is pi over 4. Arctangent t, as t is approached to infinity, that's the pi over 2. Answer gonna be pi over 4, which meaning is improper integral converges pi over 4. You're gonna say this infinity series gonna be converged, not saying they sum gonna be pi over 4. No, just we know that's converged. Let's have a second example for integral test. Integral test we're gonna use to figure out if a series is gonna be converged, diverge. First step is you have to know what is related the function to this sequence. That's gonna be ln x over x. I give the graph of this function. You see, that's gonna be this point is decreasing continuous. So we're gonna find improper integral of this function. That's gonna be bn infinity. So that's gonna be 1 and infinity ln x over x dx. So we find improper integral of this. Let's find ln x over x. Okay? So ln x over x dx antiderivative, we're gonna using new sum. You're gonna be ln x, d you're gonna be 1 over x dx. So this one is substitute integral u. ln x gonna be u, 1 over x dx gonna be du. So antiderivative u gonna be u squared plus 2 plus c. U gonna be ln x squared over 2 plus c. Now I'll plug in back here. Limit t approach to infinity ln x squared over 2, 1 and t. You plug in t first, you plug in 1. So I'm gonna plug in the t. 1.5 outside, ln t squared minus ln 1 squared. ln 1 is 0. You have ln t squared. T approach to infinity, ln t going to infinity. That's going to infinity. So what are you going to say about this improper integral that's not converged? That's going to be divergent. So we're going to say this series is going to be diverge. I want to talk about P series and harmonic series. That's very important series in the next lecture. So what is a P series? P always positive, guys. That's gonna be P series. Summation n equal 1 to infinity 1 over np, 1 plus 1 over 2p, 1 plus 3p, 1 plus 4p, 1 plus np. That's the P series. Remember that, guys. P gonna be always positive. Now, what is a harmonic series? 3 is gonna be p equal 1. When you plug in the 1 here, you see summation n equal 1 to infinity 1 over n equal 1 plus 1 over 2, 1 over 3, 1 over 4, 1 over n. Top is we say P series, especially P equal 1, we're gonna say harmonic series. Now, next slide, we're gonna investigate what happened to P series. If they are converged, they are diverge. Do you remember P integral? We did improper integral, guys. P integral this is a P integral. Here is depends on P value. This improper integral converge, diverge. P gonna be greater than 1, that's converge. P is 0 and 1 P equal 1 diverge. So this one is improper integral. So this one is related to P series right there, guys. P series, same thing, improper integral converge, P series gonna be converge. P equal greater than 1. Improper integral diverge, P between the 0 and 1, P equal 1 diverge. P3 gonna be diverge. Guys, remember that this is the P series. P gonna be greater than 1 converge. P is between 0 and 1. P equal 1 diverge. Let's have first example for those P series, guys. P series I give here 1 over n square. P value gonna be 2. P is greater than 1. This series gonna be converged. Okay? That's the P series. Another one. Summation 1 over square root 2n. Power is what? P gonna be 1.5. This one is less than 1, greater than 0. This P series gonna be diverge. Next one. Summation 1 over n square root 2n. You have find, guys, right here. You have find the P value. N square root n. That's gonna be 1 plus 1.5. 3 over 2. P is greater than 1. That's gonna be converge. Do you understand P series? Let's have more example for the P series. So summation 1 cube root n. What is P value, guys? P value is 1 over 3. That's the less than 1. That series gonna be diverge. Next one is looks are complicated. Let's simplify this term, guys, right there. So I separate square root n over n square, 4 over n square. This term is converged because P value is greater than 1. Let's simplify this one. Square root n square meaning is 1 of n square root n. This meaning is gonna be, what is P value here? N square root n. We did it, right? And P gonna be 3 over 2. So P value is greater than 1. Second series P value is 2. That's greater than 1. We say both P series converge. Then this series gonna be converged. Last one. This one. Oh, this looks weird. Denominator n plus 1. We don't worry about it. Actually, expanded sum 1 over 2, 1 over 3, 1 over 4 plus 1. What is different from harmonic series? You're just missing 1. But still, harmonic series converge. We say this still harmonic series, even though you don't have a 1. This series is gonna be diverge, guys. What do you learn in this session? Let's learn about what you learned today with the 3 big ideas. First, divergence test. Divergence test is you're gonna do first. When your limit of sequence is 0, does not exist, you're gonna say series gonna be diverge. That's the first thing you have to do it, guys, okay? Integral test, you're gonna do last. Everything is not working, you're gonna try integral test. Integral test relate to the improper integral. Improper integral is converge. Series gonna be converge. Integral diverge. Series gonna be diverge. Last one we study is P series. P series is key application. P gonna be greater than 1 is converge. P is less or equal to 1 is diverge.